Hello there, young students of chemistry. I'm going to try to get you some information while I'm out sick here. So you're going to have to be patient with my voice and do the best you can with it. I would appreciate that. So sorry. So what you have in front of you on the colored sheet of paper is a list of common oxidizing and reducing agents. You really should, as many of these as you can, you should kind of commit them to your steel trap, commit them to memory. And some of them you might already recognize if you just kind of look down the list. You can see that what you have here is some permanganate ion, and on a lot of the equations that you've balanced earlier, you were many of those reactions involve the permanganate ion. And then certainly dichromate or chromate, where the chromium is going to be reduced in those reactions. So if you'll get a look at those reducing agents, common oxidizing and reducing agents, they are not necessarily in order of how well or how good an oxidizing or reducing agent they are. They are just in order. They're just placed on there. Although I will say under the common reducing agents, the best reducing agent are your alkali metals, and then your alkaline earth metals in family 2A would be next after that. And then your multivalent monatomic cations, those transition metals, pretty good reducing agents. They really like to oxidize. And because the multivalent metals have that huge D block, they oxidize pretty well. So what you need to take notes on now are just some other redox reaction prediction that you want to think about. So we'll start here with what we called last year was single replacement. These were metal displacement reactions, and molecularly last year we would say metal plus, I'll call that metal prime, that's in compound is going to make the new metal compound plus metal prime. Actually, let me erase that. I think what we did last year is just used A plus BC. Yeah, yields AC plus B, where A was a metal in its solid state, oxidation state of 0, going to some positive oxidation state when it bonds. These reactions occur in solution, so of course now we're going to have to write net ionic equations. And last year we looked at an activity series to determine which of those metals were the most reactive, and we know that lithium is the most reactive of all of those metals. And then on and down the series, basically we could say that family 1A and 2A are the most reactive, and then as you move down those families on the periodic table, those elements get more and more reactive, so therefore they are better at oxidizing and they are better reducing agents. With those electrons in the outer energy levels that are far away from the nucleus, they are very easily removed to cause the oxidation. So here what we're saying is that we have a solid metal, we have a metal that's in compound that's been dissociated into water, so we have a free-floating metal ion. I'm just going to underline this metal so we know that this is a different metal. So net ionically, the solid metal turns into metal ion, and the metal that was dissociated in aqueous turns into the solid metal. And that is the redox reaction. This ion C is spectator, So that is not participating in the chemical reaction at all. And in the net ionic equation, that cancels out. So for example, if we had lithium reacting with calcium chloride or calcium nitrate or calcium something soluble, right? Then we know that that lithium will replace the calcium, and that would be our molecular equation. The net ionic equation gets rid of that chloride spectator ion, so we have lithium solid reacting with calcium ion to form lithium ion and calcium solid. And if you want to write molecular equations there, you can do that and then cancel spectator ions. But because it's occurring in solution, net ionic equations are required. So another type of displacement reaction that we looked at in your first year course was the metal displacement of hydrogen in an acid. And we have metals reacting with acid to form typically a soluble. You might want to think about your solubility rules here. A soluble metal compound, a salt, and then some hydrogen gas coming off of that reaction. So we have oxidizing acids and non-oxidizing acids. So when I say an acid is a non-oxidizing acid, what I mean is that that acid is going to reduce. So if we have hydrogen in its compound with a +1 oxidation state, this is where hydrogen goes from its oxidation state of +1 to the oxidation state of 0 as a gas. So hydrogen in a non-oxidizing acid, the ion becomes hydrogen gas, which is what we've written there as our molecular equation. In a non-oxidizing acid, hydrogen cannot reduce. That's kind of a lie. With a strong enough reducing agent, it can. But typically, hydrogen will not reduce. So an oxidizing acid is an acid where that element that the acid is bonded to is going to reduce. So you would have metal, which will oxidize. And then this X ion, whether it's a polyatomic ion of nitrate, or if it's just a non-metallic ion, monoatomic ion from your periodic table, it's going to reduce here. So typically you would have, of course, the metal, I'm sorry, I didn't want to write in it. I wanted to, you'd have your X ion, which is negative. And instead of reducing, that's going to oxidize to the gaseous form. I'm thinking here of your diatomic gases, chlorine, fluorine, bromine, iodine, where you would have, a hydrochloric acid, and that acid, instead of reducing, is going to oxidize. So we know that hydrogen can't oxidize, which means that that non-metal ion is what's going to oxidize here. I guess if it's not one of your diatomic gases, you might see non-metal ion just forming non-metal if it's not one of your diatomic gases. So you might want to be on the lookout for that as well. So basically what you're going to do is look at your reactants and figure out if there is something there that you know will oxidize or that you know will reduce. And if you know something is going to oxidize, then you would just find something else to reduce. Now, we know that metal can also displace hydrogen in water if the metal is a strong reducing agent, and that would be your metals of family 1A and 2A. And of course, you know, those at the bottom are going to be better at doing that than those at the top. But even calcium will replace hydrogen from water, even if the water is cold. Magnesium, not so reactive. If I were to ask you to decide of the two, I would have to give you an activity series so that you knew which metal was the most active. Later on, when we harness these redox reactions and talk about electrochemistry, you'll have a way of knowing which metal is most reactive because you'll look at reduction potentials. So that metal that has the lowest reduction potential is going to have the highest oxidizing potential, and therefore is going to be more active than the metal with the lower oxidizing potential. But here you'd have that metal forming a metal hydroxide, and then the hydrogen again would reduce into hydrogen gas. And then of course the last type of displacement reaction, we're just kind of looking at these again from last year and adding them in this year in a different way, would be if you have that diatomic halide that is bubbled into water, typically not very soluble, but we would say that it was in a solution, and then that would be the displacement of a nonmetal. So you would have, if we were using our general form here, A, where A is a nonmetal, plus BC yields BA plus C, where you'd have that metal bonding to that other, that non-metal bonding to the metal in this compound. B would be a metal, C would be a reducible non-metallic ion. So we should write that reducible non-metal ion. Lie, not a reducible, an oxidizable non-metal ion. Because here what we're having is that this non-metal is going from an oxidation state of 0 to an oxidation state of negative something in that Ba compound. So this is a reducible gas. So reducible nonmetal with an oxidizable nonmetal ion is what's going on here. The only thing you really need to look out here is fluorine. Fluorine, as an ion, is not oxidizable, so not fluorine. Never fluorine. Fluorine's going to keep that electron that it grabbed from someone else. It's going to keep it no matter what. So those are your displacement reactions from last year. The other thing we're going to look at is oxygen as an oxidizing agent. So last year we talked about combustion reactions and combustions of hydrocarbon, and that is oxygen acting as an oxidizing agent, meaning the oxygen is going to reduce to oxide ion. And then we have these synthesis reactions that we kind of looked at in your first year course. These are binary synthesis, and when a metal solid reacts with oxygen gas, you're going to get a metal oxide. So your oxygen is going from an oxidation state of 0 to -2, and your metal's going from an oxidation state of 0 to plus something, depending on the metal. Now, this compound that it produces is called a basic anhydride. That metal oxide is a basic anhydride. And I'll mention the reaction of a basic anhydride with water. It is not a redox reaction, but this is a good place to throw that in so you can look out for it. If you have a metal oxide with water, that's going to form a metal hydroxide. And you would ionize where appropriate. No ionization in the formation of the basic anhydride because, ladies and gentlemen, there is no water. And if there's no water, a substance is not going to ionize in the water, where it's not going to ionize the water. Those things sound very similar, but they are different. When something dissociates, the water is acting on it. When something ionizes the water, it is acting on the water. So a nonmetal oxide is formed in that second reaction there. And nonmetal oxides are what we call acetic anhydrides. Acetic anhydrides will react with water to make an acid. I'm just going to make a note here that this is not redox. So we cannot have changes in oxidation states here. Our metal stays whatever its highest oxidation state is. Right? The oxygen stays 2 minus. The hydrogen stays 1 plus. So no changes in oxidation state. Same thing for an acetic anhydride. If you look on the back of your list of common oxidizing and reducing agents, I gave you a list of some common acetic anhydrides. You want to remember one of them from each class. And then if you are asked to write the reaction of acetic anhydride with water, you need to pick an acid where the oxidation state is not changing. So let's look at an acetic anhydride of sulfur. If we use SO2, remember this is not a redox reaction. No changes in state here. This one is. This one we're about to write is not. Here we've got the nonmetal going. I think I'm lying to you. But because it's not ionizing, it's not redox. But the acetic anhydride, I'm going to just use sulfur dioxide. So sulfur dioxide and water. Now, we know that there are a couple of oxy acids of sulfur that we can use. We know that there is the oxy acid, sulfuric acid. That might be the only oxy acid. So in this case, what we want to make sure of is that the oxidation state of the sulfur is not changing. So we have sulfur here at a +4 oxidation state, +1 on the hydrogen, -2 on the oxygen. We can't use this one because the sulfur oxidation state in sulfate is +6. So this is not an acetic anhydride. Bad choice, Thomas. Let's start again. Let's try nitrogen. We'll do nitrogen dioxide. Dinitrogen monoxide. Nitrogen dioxide, that's fine. Oxidation state of the nitrogen here is +4. So when we add nitrogen dioxide to water, we're going to get an acid. The possible acids here are nitric acid or nitrous acid. Notice that I'm choosing oxy acids because we have to do something with that oxygen. We are not going to use a binary acid here. So let's check the oxidation states of the nitrogen, and this will tell us what our choice should be. So the oxidation state of nitrogen in nitric acid is, maybe choose 3 is 6, +5. The oxidation state of the nitrogen in the nitrous acid is +4. So because we don't want the oxidation state to change, the product that we would choose here would be the nitrous acid. I think with the sulfur, it must be SO3. Maybe I should take SO2 off the common acetic anhydride. And why don't you just scratch that out now and put on the sulfur trioxide. I know that makes sulfuric acid on the East Coast. Okay, so combustion as an oxidizing agent. Last year when we talked about combustion, we only talked about the complete combustion of a hydrocarbon, where the products were a constant carbon dioxide and water. This year I want you to know the truth of what happens when a compound is not uh, completely oxidized by the oxygen. So in the case of what we learned last year about the complete combustion of a hydrocarbon, the oxygen is plentiful and can completely reduce the carbon from whatever, can completely oxidize the carbon into its oxidation state of 4 plus. Oxygen here is reducing, carbon is oxidizing. So if you think about it, in order for the carbon to oxidize, the oxygen has to take electrons away from it. So if we don't have enough oxygen, not all of the electrons in the carbons that are present are going to be removed. So what happens then are we have products that are not carbon dioxide and water. So if we have a limited amount of oxygen, instead of getting carbon dioxide, we get carbon monoxide. If we're looking at this visually, we would go from a blue-colored flame to a yellow-colored flame. The oxygen is still reducing to its 2 minus oxidation state, but this time, instead of the carbon going all the way to 4 plus, it's only going to 2 plus. So the carbon, instead of giving away 4 electrons to the oxygens, has only given away 2 electrons to the oxygens. So it doesn't oxidize to its highest oxidation state of positive 4. And then if we have oxygen in a very limited state, oxygen is still going to reduce, but our products now become just straight carbon and water. So the oxygen, -2 to 0, and the carbon goes from whatever negative number this is. I don't know that it's a 4. Some negative oxidation state on the carbon. We could calculate it, I suppose, but I've got to be honest, I don't want to. So this is going to be some negative oxidation state here. And it's going to oxidize to 0 in carbon, and this is what we call soot. So when you have, a fireplace and your chimney gets filled with black ash, that is soot from the very limited combustion of whatever hydrocarbon is found in the wood or whatever fuel it is that you're using. So as oxygen gets limited, there's not enough oxygen to remove 4 electrons. Well, I shouldn't say 4 electrons, because depending on the state, this carbon could have an oxidation state that's really, really low, depending on our subscripts here in the hydrocarbon. But there's not enough oxygen to remove all the electrons to oxidize the carbon into the positive 4 state. And then we would get the positive 2 state of the carbon monoxide, and then finally the 0 oxidation state of the solid carbon buildup. So those are the 3 reactions I really kind of wanted you to look at there, outside of learning your aqueous common oxidizing and reducing agents, which is what we've been looking at really closely. Anything that we've balanced has been in solution, unless it was balancing by change in oxidation state. I'll predict a couple of products with you here, if you'll bear with me for just a few more minutes. And then I have an assignment for you to work on, a problem set called more REdox. It's got some reaction prediction on it and some other general redox information, which you might have to get from your interaction with your textbook. I'm not going over all of this information with you, so hopefully you're having some good interaction with your textbook. So here we have a problem, and immediately I see the permanganate ion, and that just sets off an alarm in my head. Hey, this is a redox reaction. And not only do I have permanganate, I have a multivalent monoatomic cation of iron. So we know here that the oxidation state for iron is 2+. We know that metals typically do not reduce, and we know that the highest oxidation state for iron is 3+. So probably what's going to happen here is that this iron is going to oxidize to an oxidation state of 3. And at some point you'll put in your steel trap that a permanganate ion likes to reduce to manganese 2+ ion. So if we are writing the net ionic equation here unbalanced, potassium and chlorine would be spectator, and you'd have permanganate ion reacting with iron 2 ion to form iron 3 ion and manganese 2 ion. And then you would balance that using one of the methods that we have discussed before. It doesn't say, oh, it does say that it's occurring in acid, so you would break that into the half reactions and balance in acid. I'll let you guys do that yourselves, and then you can check with each other, but do take a minute if you want to pause now and balance it, and then check, and then move on, or, once this is through, balance them and check with each other to see that you got the balancing correct. Number 2, we have a displacement reaction, silver. Now when you see this word dilute, that's going to be a key word to indicate that this is a redox reaction. So if you see the words hot and concentrated, or if you see the word dilute, that's going to tell you, hey, I should think about those common oxidizing and reducing agents. And if I look at my list, I can see that dilute nitric acid can act as an oxidizing agent while it reduces to nitrogen monoxide gas. And because that is itself an acid, we will balance in an acid. So the nitric acid here is reducing. It's actually the nitrogen is the species that's taking those electrons. So we have an oxidation state of +5. Silver is 0. Silver is not a very good thing to oxidize, but it will, and it will oxidize to its positive state. Remember that silver, even though it's in the D block, is not multivalent. So those are the products we have. And then we would see that nitric acid, because this ionizes as a strong acid, the hydronium is spectator here. And we would get rid of that. So your net ionic equation would be solid silver reacting with nitrate ion to form nitrogen monoxide gas and silver ion. So this would bubble until the reaction was over. And again, I would break this into your half reactions and balance it in acid, because one of the reactants is an acid. Here we have the combustion of copper. So this is really rusting. I mean, anytime you have a metal that's reacting with oxygen, this is rust. That's why rusting is also called oxidizing. So we know that metals will react with oxygen to form solid metal oxides. Now copper can form a 1+ or a 2+ oxidation state. If you have to choose, you should always choose the highest oxidation state for the multivalent metal. If you look on the back of your list of common polyatomic ions, I put on there the common oxidation states for the multivalent metals. We're going to use the rule of thumb that metals will go to their highest oxidation state. So I would predict CuO instead of Cu2O. And then, of course, balance by inspection. There's no water here, so we're not going to ionize anything on this reaction. last one here is potassium nitrite. That's a salt that ionizes, and potassium is going to be spectator. And then we have potassium dichromate, which also ionizes in water, and potassium will be spectator. So when you have the dichromate ion, again, that should be a real indicator here that this is probably a redox reaction. And dichromate in it says in a base, dichromate in an acid or a basic solution is going to go to chromium 3+. You may have recognized that from some of the equations that we've been balancing. So dichromate goes to chromium 3, and then the nitrite ion in base is going to go to the nitrate ion. So here what we have is chromium. So there's some ways to kind of put these in your head without actually memorize them. So we know that chromium is going from an oxidation state of 6+ to 3+. It is reducing, which means we need this to oxidize. What is likely to oxidize is the nitrogen. So we have oxygen at an oxidation state of 2-, and nitrogen is at -2 times 4 is +3. And we know that if nitrite turns into nitrate, that the oxidation state for the nitrogen is going up to +5. So that's really the best choice here. I'm going to be honest, I would think that the College Board, as long as you had the chromium reducing and something oxidizing from that nitrate or that nitrite ion, they give you credit, although potassium cannot oxidize, so you cannot choose that. You cannot choose a group 1A metal to oxidize from its 1+ state. It cannot do that. It has no room in its electron configuration to do that. So you'd have to have that nitrogen oxidizing, and I don't know what else you would oxidize it to, but you could think that through. There might be something. So then, of course, your net ionic equation is nitrite ion reacting with the dichromate ion, yielding chromium 3 ion, and then the nitrate ion. Most likely the indicator of the chemical reaction that would be visual here would be a change in color from like an orange yellow, from a yellow, sorry, to an orange color of the chromium going from 6+ to 3+. But again, if you want to balance this, you would divide it into its half reactions and balance in acid. Oh, for Pete's sake, balance in base. All right, last one here. Actually, no, there's one more after this. So you would have hydrogen peroxide. You've got to be careful here because remember the oxidation state for oxygen is -1. Oxygen really does like to be -2. So it's probably going to turn that hydrogen peroxide into water where the oxidation state is -2. So the oxygen is reducing, which means we need something here to oxidize. We know that potassium under no circumstances can oxidize. It's already at +1. It cannot oxidize any further. That will not happen. As a matter of fact, it will not reduce either. So then we have iodide ion, which could oxidize to its elemental form of the diatomic iodine gas, and that would be the best choice there. So you'd have hydrogen peroxide reacting with iodide ion to form water and iodine gas. Iodine gas is a purple gas. That would be the indicator, the visual indicator of the reaction. You'd have bubbling and a purple gas evolving. And if you're standing right over it, you'll probably die. Iodine is pretty toxic to the human body in its gaseous state. You're going to want to suck that outside, kill the birds, put in a fume hood. You don't want to be breathing much of that in. Iodine poisoning is a pretty serious condition. I think it just starts with some nausea. Okay, and then the last one, is not here. Let's write it in. Where you would have the displacement of a metal, and then aqueous hydrogen gas. Magnesium reacts readily with hydrochloric acid, and hydrochloric acid is going to form hydrogen gas, and then we're going to have magnesium ion. If you wanted to write it molecularly, you would have magnesium chloride, and then of course you would ionize this, your strong acid, right? So you'd have magnesium solid, piece of solid shiny metal. It's easier with these to write the ionization of the acid as H plus instead of H3O, although you can write it as H3O. And then you have your ionized magnesium chloride, and you can clearly see here that the chloride is spectator, balanced by change in oxidation state. Okay, that's what I have for you. I think it went pretty well, considering. Enjoy predicting products and working on redox reactions. Bye.